So here we're going to look at our first substantive geometric sequence example. Okay. So suppose that the sequence starts like this. A1 is 4, in other words, the first term is 4, A2 is 6, A3 is 9, and that each subsequent term comes from multiplying the term immediately previous by 3 halves. Okay. So this is going to be our geometric sequence of interest to us. So you can see that 4 times 3 halves is 6. 6 times 3 halves is 9. And so you can see that this is in fact a geometric sequence with common ratio 3 halves. Okay? Right? This is a geometric sequence with common ratio 3 halves. So now let's list out a few terms and see if we can see anything that catches our eye. Okay? So let's look at it this way. So we know that A1 is equal to 4. We know that A2 is equal to 3 halves times 4. Okay. And we know that this gives us 6. Okay. How do we know that? We know this because of the following fact. If I have 3 halves and I multiply it by 4, well, first of all, we can't multiply it directly there because 4 is not a fraction, but I can easily turn it into a fraction by setting it as the numerator and 1 as the denominator, as follows. 3 halves times 4 over 1. Okay. Now, can we multiply them? Yes. And we remember that when we multiply fractions, the product of two fractions is the fraction whose numerator is the product of the numerators, in this case 3 times 4, which is 12, and whose denominator is the product of the denominators of the fractions, in this case 2 times 1, which is 2. What's 12 divided by 2? That's going to be 6. Okay, so in fact we see that that's the case. We see that A3 is equal to 3 halves times 6. Okay, remember, we get the subsequent term by multiplying the term immediately previous by 3 halves. What's the term immediately previous to this one? 6. What's 6 times 3 halves? That's going to give us 9. And so that's how we got this one, and so on and so forth. Let's get the next term. The fourth term of the sequence is going to be, let's say, 3 halves times the previous value, which is 9. Okay. What is that? Well, that's going to be 27 over 2. Okay. Now, I want to make some observations, okay? Let me do this calculation for you real quick so that you can see that, and then we're going to do an observation, okay? So, what is 3 over 2 times 9, okay? Well, again, 9 is a whole number, so we can't do the multiplication yet, but we can convert the 9 into a fraction by setting it as the numerator and 1 as the denominator. So this is going to be 3 halves times 9 over 1, okay? Now we can do the multiplication. We know that to find the product of two fractions, we form the fraction whose numerator is the product of the numerators, right, of the two fractions being multiplied. So 3 times 9 is 27. And whose denominator is the product of the denominators of the fractions being multiplied, in this case 2 times 1, which is 2. So you can see that that's in fact, the fourth term of this sequence. Okay, so now what I want to observe is the following. I want to look at the following situation. What is A2 divided by A1? A2 divided by A1 is equal to 6 divided by 4. And what is that? That simplifies to 3 halves, right? Because if you divide the top and bottom by 2, you get 3 halves. That's interesting. What if we have A3 divided by A2? A3 is 9. A2 is 6. If I divide the top and the bottom by 3, what's 9 divided by 3? That's 3. What's 6 divided by 3? 2. Interesting. Look at that. And what happens if I do A4 divided by A3? Well, we will get 27 divided by 2, right? Divided by A3 is 9. So now we're dividing a fraction by a whole number. We can't do that, but we can make the whole number in the denominator fraction, again, by setting it as the numerator and 1 as the denominator. So for example, I can replace this as 27 over 2 divided by the fraction 9 over 1. Now, whenever we divide by a fraction like 9 over 1, we're going to multiply by the reciprocal, right? So this is going to become 27 over 2 times 1 over 9, because that's the reciprocal of 9 over 1. And now we can form the product of these two fractions, right? So 27 times 1 is 27. 2 times 9 is 18. Oops. And you can see, aha, if I divide the top and the bottom by 9, 9 times 3 is 27, and 9 times 2 is 18. And we get 3 halves once more. So if we were to extrapolate from this pattern, what you can see is that an divided by an minus 1, in this case, for this example, is 3 halves, okay? And of course, I'm assuming here that n is bigger than 1, okay? Because you can see that at n equals 2, that would be the a2 over the a1, which is what we saw here. If n equals to 3, then it's a3 over a2, and in fact equals 3 halves. And we can see that that continues forever. In fact, you can see that more clearly if you just look, well, we'll look at that when we got the recurrence relation. But what I wanted to show you here is that this is why we call the number that we're multiplying that's why we call, for example, this number, the 3 halves, a common ratio. Because if you take the ratio of each, if you take any two consecutive terms from a geometric sequence, and you take the forgive me one second. If you take any two consecutive terms of the sequence, if you take the one with the larger n value, in other words, like let's say a3, and you divide it by the one immediately previous, if you take, okay, that's a perfect way of saying it. If you take any two consecutive terms of the geometric sequence, and you divide if you divide the, oh my god, if you divide the term of the sequence by the one immediately previous, you will get the same ratio, and that ratio is the common ratio, because it's common to every pair of consecutive terms in the geometric sequence. Okay? Oh my god, what a mouthful that was, or what a confusion that was. And so that's why it's called the common ratio. Okay? So that's the first observation that I wanted us to make. Okay? So now what I want to do is I want to look at this list of values, and I want to look at it through a different lens. Okay? Okay. So what lens do I want to see it through? Well, look at from A1 to A2, you can see I got A2 from multiplying 3 halves times 4. Can I rewrite that differently? Yes. Right? I can say in this case that A2 was equal to 3 halves times the A1. Right? Look at the A3. Look at this. A3 is equal to 3 halves times 6. What is 6? That's A2. Right? So A3 is equal to 3 halves times A2. You see? And then, of course, you can see that in this case, the A4, the fourth term of our sequence, is 3 halves times 9. What is the 9? A3, or the third term of the sequence, right? And so from this, we can extrapolate that, and we can say, aha, the nth. So first of all, the first term is A1, which is 4. And then the nth term of the sequence, right, will be 3 halves times the n minus 1 term of the sequence. Okay? And so what we can observe here is we can observe the recurrence relation formulation of this sequence. Okay? Okay. So let me write that one down here. Right? And we recall that a recurrence relation is a way of specifying a sequence where we have some initial value or values, depending on the kind of recurrence relation, and we have some rule that allows us to get the next term in the sequence based on that previous value or those previous values, depending on what the case may be. In the case of the arithmetic sequence and in the case of the geometric sequence, we only need to know one previous value to calculate the subsequent term of the sequence. Okay? Now, let me also make a brief point here. If we have the recurrence relation, we can immediately see what the common ratio is. Because look, if I take this part of the recurrence relation and I divide by the an minus 1, I get an over an minus 1 is equal to the 3/2. Okay? So you can see that more clearly here if you have the recurrence relation, what the common ratio is. Okay? And so now finally, I want to make another observation. Okay? So let's do that together. And I'm pretty sure by now you guys can see what observation I'm going to make, right? But let's do it together anyway. So let me just rewrite these terms of the sequence in such a way as to reveal what we're getting at. The first thing is, the first term is 4. That's it, okay? We don't have to say anything more about that. What about the second term? We can write the second term of the sequence, A2, as, well, 4 times 3/2. Okay? We're going to, now, what is the third term of the sequence? The third term of the sequence we get by multiplying the second term of the sequence by 3/2. Now, what does that give us? That gives us 4 to the 3/2 times 3/2. Okay? Right? Now, of course, I could have simplified this, and I would have gotten 6, right? And then I would have gotten 6 times 3/2, and that would have given me 9. But if you'll notice, by not simplifying it, I'm able to start to see a pattern developing here. The next term in the sequence, A4, would of course be 4 times 3/2 times 3/2, because that's the previous term, and then times 3/2 again. And of course, by now, I think you guys can see the pattern. I can write this as 4 times 3/2 to the third power, in this case 1, 2, 3, or in other words, if you can see the pattern, 4 minus 1, right? But let's write it as 3 for now, okay? Look at this, 4 times 3/2 to the square. What about this one? This one is 4 to the 3/2 to the 1 power. And we know that if we have some value, some real number x, and we raise it to the 0 power, it's equal to 1, right? That's one of our exponentiation rules. So I can also write this one as 4 to the 3/2 to the 0. And if I look at this pattern, I can see, aha, my nth term of my sequence, okay, can be written as 4 to the 3/2. And notice the pattern we mentioned earlier. Here, this is the fourth term of the sequence. Look at the power of the 3/2 of the common ratio. It's 3, which is 1 less. Look at the third term of the sequence, A3. Look at the power on the common ratio. It's 2, which is 1 less. So here, I'm looking for the nth term. What's the power going to be in the common ratio here? N minus 1. So now I have I've calculated here the term, an explicit formula for the nth term of this geometric sequence. And as we saw before in the arithmetic sequence example, you know, if we wanted to calculate, let's say, the 100th term of the sequence, okay, we knew that if we were doing an arithmetic sequence, we would have had a ton of calculations to do to get there, right? Same thing here. If we wanted to calculate what the 100th term of this is, we would have to multiply by 3/2 over and over and over and over again. But if we want to find the 100th term, but if we have this formula, which you saw me construct for us here, we can easily calculate the 100th term of the sequence. Now, in actual fact, to actually get the numeric value might not be that easy, okay, for reasons that you're about to see, but we can definitely write an accurate expression for what that number is, okay? What do I mean by that? Well, I want you to look at this expression for a moment, okay, and let me get rid of this now that we don't need it anymore. Okay. So let's say I wanted the 100th term, right? The 100th term of this sequence would be equal to 4 times 3/2 to the 100 minus 1, which is 99, okay? What is that? Well, that's going to be 4 times 3 to the 99th power divided by 2 to the 99th power, okay? So we could leave it like that, of course, or we could go further. We know that 4 is 2 squared, right? Because 2 times 2 is 4. So I can see that this is 2 squared, and I can write it actually as 2 squared over 1 times 3 to the 99th power divided by 2 to the 99th power, right? And I can see this, and I can see, aha, that's going to be 3 to the 99th power on top divided by 2 to the 97th power. Because these, if we look at the 2 squared on top, that's like 2 times 2 on top. And if I look at the 2 to the 99 on the bottom, that's like 99 2's being multiplied on the bottom. The 2 2's on top cancel, let's say, with 2 of the 2's from the bottom, leaving us with 97 remaining 2's on the bottom being multiplied, which is exactly this. So now, to actually calculate the value of 2 to the 97 or 3 to the 99 is a very, very non-trivial thing, okay? But I have an accurate and correct expression for the numerical value of the 100th term of the sequence, and I calculated it in a few seconds with the rules of algebra based on the formula for the nth term of the sequence. Okay, so let me just recap what we talked about. We started off with a geometric sequence. We examined the way that a subsequent term was related to the previous term. And we saw that if you take a subsequent term in this geometric sequence and you divide it by the term immediately previous, we end up getting the common ratio. And we know that that's why it's called a common ratio. Because for any pair of consecutive terms in the sequence, the subsequent one divided by the previous one always will simplify to the common ratio. Okay? And if that were not true, then it would not be a geometric sequence. We saw that. And that's number one. Number two, we saw that we could recover the recurrence relation from observing the way that the table was built up, as we saw observing the pattern in the sequence. We then observed that by looking at the pattern in a different way, by not carrying out the calculations and seeing what the calculations began to look like, they formed a pattern that allowed us to deduce the formula, an explicit formula for the nth term of the sequence. And then finally we saw that we could use that explicit formula to calculate, for example, in our case, the 100th term of the geometric sequence of interest to us right now. Okay? And in any case, I hope you've enjoyed this example, and I look forward to seeing you again soon. Thank you so much.